Hello everyone, welcome back to part 3 of our tutorial series. Today we will be addressing the remaining part of the combustor, that is primary injectors and the intake duct. Open the topology that was saved at the end of part 2, which has the topology for the secondary injectors and aft cavity duct. Here we have the primary injectors at an 15-degree angle to the duct surface, unlike to what we had seen in the secondary injector. Create the whole topology using the same approach which was used for secondary injectors, that is, select the top, bottom and whole surfaces in 3 different empty surface groups. Open the whole topology tool from the topology tools drop-down at the top and provide the inputs. Give C9 or any empty corner group to add peripheral faces. This will group the outermost faces in the given group, which will be handy when extending the topology. Save the topology. Corner group C9 has the outer corners grouped together. Click on C1 and add the faces from C9. Now, erase all the faces from C1 except the faces inside one of the cylinders that encloses the injector. We will use C1 to wrap outwards, which will create an O-type grid when assigned to the cylinder. But before that, we exclude the bottom face from wrapping, so add that bottom face in group C2. Now click on C1 and click on wrap. Select the boundary wrap with exclusion group as C2 and apply. Adjust the wrap position to keep the wrap layer outwards. Assign the respective faces. Now, repeat the above steps for another cylinder as well. Save the topology. Clear the corner group C1 and add the faces from C9 again. Retain only the outer faces which are inside the duct using the retain selection button under the corner group selection. Clear the group C2 and add faces from C1 and retain the faces from one side. Select the surface with ID 2 and copy those to the surface. Repeat it on the other side faces as well. Link the topologies around both the injector sides and assign the faces to the respective boundary surfaces. Similarly, group and copy faces to the inlet boundary and towards the cavity region. We now need to link the two topologies, which is the one for the aft cavity secondary injector and another that we now have created. To link both the topologies, both the adjacent sheets shall have equal number of faces for one-to-one phase connection. The number of faces in each group appears in the status bar when we click on the desired corner group. To match the number of faces, insert the sheets as shown. Once the number of faces in both the corner groups are same, link the faces and save the topology. Validity check highlights that there are some missing surface assignments. Assign the faces to respective surfaces. Also, we notice that there are some extra faces assigned to the surface 24, which was supposed to be assigned to surface 5. So erase the extra faces from 24 and assign them to surface 5. Repeat this for the surface 23 and surface 0 as well. Validity check reports that the edges emerging from intersecting surfaces need support surfaces, which is known as mildly severe singularity and is highlighted by yellow color. This singularity is fixed by creating an internally supporting surface. This surface holds the corner sheet which bisect the sharp convex angle at the intersection. We can see the grid generated with mildly severe singularity. There are two ways to avoid the bad quality cells. 1. Balancing the density. 2. Holding the corners by assigning it to the internal support surface. We will discuss the second approach since once the corners are assigned to the internal support surface, they will be fixed and will be independent of the density change anywhere in the domain. Learn more about the mildly severe singularity from our YouTube channel. Open a new window and load the surfaces. Group the intersecting surfaces in an empty surface group and extract the corners at the intersection of surfaces. Create a ribbon using both these chain of corners such that the ribbon bisects the convex obtuse angle created by the surfaces. Group the corners as shown to create the internal support surface using Control-Net Surface tool under the Surface tool drop-down menu. Give any suitable name to the surface and click Apply. Load that internal surface into the current topology. And assign the corner sheet as shown. This removes the mildly severe singularity. Group the assigned sheet and do an internal wrap with insert, which will split the block in two and automatically assign the inner sheet to the surface. This internal wrap will ensure that there are one-to-one connected blocks to the sheet assigned to the surface to avoid stretching up cells. Note: if the internal wrap is not done, then there will be 3-point singularity assigned to the surface, which is also known as mediumly severe singularity. Don't forget to change the orientation of our internal surface to interior, that is, two-sided surface, either through surface settings or by right-click type interior. Validity check reports that the topology is valid with no singularities. Save the topology. For faster grid conversions, we will run the initial grid only on a partial topology. Create a plane and assign the corner sheet as shown, which will act as a temporary boundary for the partial topology. Change the orientation of the surface to interior and select the wireframe on the right hand side in the corner group C1. Now, run the grid with half density for the partial group C1. After 2000 sweeps, the grid is smooth. Align the wireframe in group C1 to the generated grid using Align to Partial G-Grid Group option. This will update the position of the blocks in the topology as per the smoothened grid blocks. Run the grid with default density for the full wireframe. Here, we can notice that the grid in the right side region is already smooth, and the grid around the primary injector opening is squeezed and requires improvement. Move the sheets using edge length option as shown. Add an insert as shown and select the highlighted sheet to do an internal wrap. it is seen that the selected sheet is split into two sheets. Also, we shall hold the movement of blocks by creating planar surfaces and assigning the sheets as shown. Don't forget to change the orientation of these surfaces to interior, that is two-sided. Validity check reports a valid topology. To save our time, we will run the grid only on the region that we are improving. So select the wireframe in a group, run the grid on that group with the default density. Notice the improvement in the grid around the injector opening. Also notice that the straight sheet which was holded by planar interior surfaces. Align the wireframe in group C2 with the partial grid group. We shall go ahead and do the local refinement for the region around the injector opening using Tensify tool under nesting. Delete the planar surface that we had created to hold the block movement. Select the wireframe as shown. Use the densifier with refinement level 2. This will create the nesting in one step, unlike how we did in the secondary injector part with the area nesting. Again, run the grid on partial wireframe group for half density for faster conversions. Once we get the smooth blocks, align the topology to the partial grid group. Now that we have smooth block placement everywhere in the topology, go ahead and run the final grid. Run the grid for around 1000 sweeps. Load the final grid in the UI. Create the slices to check the interior grid. The final grid has a good quality uniform cell distribution. Also notice the locally refined nesting structure for all the injector openings. Thank you for watching. If you like this video, leave us a like and subscribe to the channel for new videos. If you have any questions or any comments, feel free to leave it below. If you want us to post tutorials on any specific geometries, you could write to us on support@gridpro.com.